Hey everybody, this is Atomic Structure for AP Chemistry in 10 minutes or less. This video is meant as a refresher that's only going to cover some of the major topics in Unit 1 of the 2021 version of AP Chem. It's intended for students who've already learned the material and are beginning to prep for the AP Chem exam. For anybody that cares, it covers these exact topics from the AP Chemistry course and exam description. The things it doesn't cover, I'm either just not going to talk about or will be covered somewhere else in a different video. Let's get started. So of course, the atomic structure unit, it's all about atoms and the subatomic particles that make up those atoms. We should probably start by saying that atoms come in all sorts of different types. We call different types of atoms elements, like the element boron, symbolized here with a capital B. What makes this an atom of boron as opposed to a different element is the amount of protons in its nucleus. Boron in particular has 5 protons, which we denote here with a 5 in the bottom left-hand corner. If this boron also had 5 neutrons in that nucleus, that would give it an atomic mass of 10. Each proton and each neutron counts for 1 atomic mass unit. 5 plus 5 adds up to 10. And what we've just written is called the isotopic notation for boron. It's a notation style that describes the nucleus of the atom. We should point out that this is not the only form that boron comes in. Here's a different boron atom, also with 5 protons, but this time there's 7 neutrons for a total mass of 12. When you have different atoms that have the same number of protons, like these both have 5 protons, with different numbers of neutrons, here leading to different masses, there's a name for those types of atoms, and they are called isotopes. These in particular are 2 of the common isotopes of boron. One of the ways that we know these isotopes exist is from an experimental process called mass spectrometry. In mass spectrometry, there's an instrument called a mass spectrometer where you can inject a sample of atoms and it produces a graph that plots the numbers of atoms with certain masses divided by their charges. Now, the most common charge that an atom is going to have as it goes through a mass spectrometer is +1. So if I was to inject a sample of boron atoms, some of them have a mass of 10. So I'm going to see a peak plotted at 10 divided by +1. And the height of this peak is going to correspond probably to a percentage that boron atoms with a mass of 10 made up in the sample that I injected. Some of those boron atoms also had a mass of 12, so I might see a different peak plotted at 12. Since the peak is lower, that means a smaller percentage of those boron atoms had a mass of 12. You might also notice on this mass spectrum some smaller peaks at, say, 5 and 6. You might notice that 5 is exactly half of 10, 6 exactly half of 12. Those are probably the same boron atoms with masses of 10 and 12, except they fall at 5 and 6 because those atoms were ionized to a +2 charge. 10 divided by 2, of course, gives me 5, and 12 divided by 2 would give me 6, although that's less common, so you'll see smaller peak heights for these +2 charged borons. So isotopic notations in mass spectrometry tell us about the nuclei of the atoms. We also need a tool to describe the electrons that surround that nucleus. To do that, the most common method is writing something called an electron configuration. To write an electron configuration, I'm a big fan of something called the diagonal rule, where I make out a list of all the different orbitals those electrons can fall in, S's, P's, D's, and F's, and their corresponding energy levels, 1st, 2nd, 3rd, 4th, 5th, and so on. From this, you simply draw a series of diagonal arrows through the orbitals. The order in which those arrows pass through the listed orbital tells you the order that you'll fill electrons into those orbitals when writing a configuration. 1 s orbital first, 2 s orbital second, followed by the 2p, then the 3s, then the 3p, then the 4s, then the 3d, 4p, and 5s, and so on. We also have experimental evidence that these electron orbitals exist from something called photoelectron spectroscopy, or PES for short. Photoelectron spectroscopy also produces a graph similar to mass spec like we just talked about, except this time it graphs the quantities of electrons with various binding energies. And binding energy you can think about as the amount of energy it takes to remove certain electrons. This is also sometimes referred to as ionization energy. So if the spectrum looked like this, we've actually got the highest ionization energies on the far left. These are the electrons closest to the nucleus and hardest to remove. Therefore, the first peak on the left typically represents the 1s orbital electrons. Moving out from there, further from the nucleus, we've got the 2s orbitals. Notice the heights of these two peaks are the same, indicating those orbitals hold the same amount of electrons, and you might even remember that quantity. S orbitals can hold 2 electrons apiece. After the 2s, we've got the 2p orbital, or orbitals. This peak is approximately 3 times as tall as the s peaks, and that's because p orbitals can hold 3 times as many electrons, 2p6. This particular spectrum then stretches out to 3s2, 3p6, which I can then use to identify the element. It's the element with 18 electrons, otherwise known as argon. And last but not least, there's a giant component of Unit 1 that has to do with something called periodicity or periodic trends. This term refers to various predictable atomic properties that change in regular ways as you move up and down or left to right on the periodic table. For the AP Chem exam, it's a good idea to simply know what those trends are. I like to remember them based on the different corners of the periodic table. This bottom left-hand corner, those are going to be the atoms that have the largest radii. That means as you move down any column, the atomic radius will increase from one atom to the next, or as you move right to left, the atomic radius will also increase, meaning the bottom left-hand corner, those are going to be the largest atoms on the periodic table. There's lots of other atomic properties that change, increasing towards the other corner, this time the top right-hand corner. These include ionization energy, electronegativity, and electron affinity. That means for any of these 3 properties, like ionization energy, as I move from bottom to top within a column, the ionization energy increases, or as I move from left to right within a row, the ionization energy is going to increase in that direction as well. Now, simply memorizing these trends is only going to get you so far on the AP Chem exam. Chances are pretty good most of the time you'll be explaining why these trends exist the way they do. So whether you're explaining the trend in radius or ionization energy or even electron affinity, it almost always boils down to this one idea of the Coulombic attraction between the outermost electrons in the nucleus and whether that attraction is strong or weak and what the strength of the attraction is caused by. And there's various factors that can affect the strength of that attraction. The first one is the distance from the nucleus. If an electron is farther from the nucleus, it's going to be more weakly attracted to it. Secondly, we've got nuclear charge. That's simply the charge of the nucleus as determined by the number of protons. If the nucleus has 9 protons and compared to a different nucleus with only 7, the 9 protons has a greater charge magnitude of +9, and that means electrons in that atom are going to be more strongly attracted to the +9. Electrons will be more weakly attracted to the +7. And lastly, we've got something called shielding. This has to do with the electrons that are actually in between the nucleus and the outermost electrons. These in-between or inner electrons, let's call them, they can actually cancel out some of that positive charge, some of that nuclear charge that the nucleus has. So the more inner electrons there are, the greater shielding they cause, and that's going to lead to outer electrons that are more weakly attracted to the nucleus. You can also combine this nuclear charge and shielding effect into one consideration called the effective nuclear charge. The effective nuclear charge takes into consideration the charge of the nucleus by itself, but then subtracting out the shielding inner electrons and how much of that positive nucleus they cancel out. And that wraps it up for atomic structure for AP Chemistry in 10 minutes or less. Thanks for watching.